So we're going to talk today about a joint paper I have with Dylan Airey, Normality of Different Orders for Cantor series expansions. And I'm going to give a little bit of background and motivation for some of what we're talking about. So our idea of a normal number in base B is that all the digits and blocks of digits really kind of show up at random what they should be, as often as they should be. And the idea of normality was, and I'll just define it precisely in a second, the idea of normality was introduced by Burrell in 1909. So in his paper in 1909, where he proved the strong law of large numbers, he defined normal number, and he proved that Lebesgue almost every real number is normal on all bases, but he had a different definition than we're used to. So I'm going to build this up from the beginning and kind of say what Burrell said. So I want to give a different definition to start with. We say that x is simply normal in base B if each of the digits say 0, 1 up through b minus 1 occur with frequency say 1 over b and the B Airey expansion of x. So an example, so it's not really too hard to come up with simply normal numbers. So for example, points 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 repeating in base 10. All right, so Burrell's definition of a normal number in base B is as follows. Burrell says that x is normal in base B if x, bx, b squared x, and so on are all simply normal in the bases say b, b squared, b cubed, and so on. Okay. So using this definition, it's not too hard to see how you could apply the strong law of large numbers to show that, let's say normal in base B, to show that Lebesgue almost every real number is normal in base B, and then from there, just through the countable intersection property, you can show that Lebesgue almost every real number is normal in all bases. Now, we got to really kind of see what this is actually saying. So let me just give an example to start out with. Let's say we have something like x is equal to pi, which is say 3 point, we're not going to go too far out on this. We just want a few of these just to kind of see what's going on here. So what does it mean? Okay, if this is x right here, so if we want to multiply by, let's say, b squared, for example. So in this case, we have b equals 10 because this is base 10. So, so 10 squared times pi is, right, 314.1592653 and so on. Okay, but what about this being, say, simply normal in base b squared? Well, what happens, okay, base b squared, that's base 100. So pi in base 100, or 10 squared times pi, in, say, base 100, say 10 squared. Well, let's just have this 314. We don't really care about what happens over there, but what is this? This is 15. We have the digit 15 because we're in base 100, we're grouping these together. We have 1592. 65, and so on. So what we're really saying is all the digits 0 through 99, remember these are individual digits because we're in base 100, are going to show up with frequency 1 in 100. And so what we're really saying is, okay, if you look at all these places, all these digits are showing up as often as they should. Well, let's go back to the original number and see what we're looking at. So 15, what's happening here? That's the third position. 92, that starts at the fifth position. 65, 92 starts at rather the fifth position. 62 starts at the seventh position, and so on. What we're really doing is we're counting blocks of length 2 at odd positions. Okay? So you can fiddle around with this and change these bases and the shifts and everything. And what you're really getting is that Burrell's definition is really a notion of AP normality, meaning normality along the arithmetic progressions. Right? So what we're going to really do is we're going to call this AP normal of type 1. Right. And I haven't written down the current definition we have of normality yet, but it's pretty obvious that you're going to get an implication in one direction. But I want to remark that we're using pi as an example here. Of course, this is a totally open problem. Is pi normal in any base? I mean, it probably is, but who knows? We're certainly nowhere near a proof of this. So, so this was the original definition of normality. Now, I want to say that this was way later, 1951. This is Niven and Zuckerman. So, theorem. We know that x is, say, normal in base B, say in the sense of Borel. If and only if, for all blocks B, the number of the block B shows up with frequency. That's going to be 1 over the base B to the length of the block B. So what we're really saying, and this is really our more familiar definition of normal number, that all blocks are showing up kind of as often as they should. And this wasn't really a completely trivial thing. I mean, it turns out there have been some simplifications since this was originally proven, but this is still a number of years later, and there are a lot of people that kind of assume this equivalence without proof. Copeland, Erdős, Sierpinski, and several others. And this is mentioned in Jan Bajot's book, talks a bit more about this. But the point is that it's kind of a subtle thing, because I think some people might look at something like this and say, okay, well, what happens along the arithmetic progressions and just kind of in the sequence as a whole, I mean, it should probably be kind of the same thing, but it really isn't. So I want to mention another result. So this is due to Fürstenberg. And this is in his seminal paper on disjointness in ergodic theory. So he claimed to have an alternate proof, basically just sort of immediate, using the material he developed in this paper of Niven and Zuckerman's theorem. And what he really did was he had just a completely different notion of normality along arithmetic progressions that he showed was equivalent. So what he basically showed was, let's say let x equal point, let's say d1, d2, d3, and so on. And let's say that's in base B. Then x is normal in base B. If and only if the sequence points dr, dm plus r, d2m plus r, d3m plus r, and so on, is normal in base B. For all m and r. So really what we're doing is we're saying take this real number here and write the digits along arithmetic progressions. And so if these are normal for every choice of arithmetic progression, that's equivalent to being normal just in base B. And why is this a different thing? We'll take pi as an example again. So we're just going to write it again. And let's suppose we do something like we did before. Let's say we want to look at blocks of length 2 along, I think we're using odd positions. Okay. So if we're looking at odd positions, right, we would pick m equals 2 and r equals 1. So that's the right arithmetic progression. And so the number we get by copying this down is going to be 0.11963, and so on. Okay, so let's say we want to test a block of length 2 to see if it shows up here with, say, the right frequency. Well, we test it against 1, 1. Well, this is position 1 and position 3. Okay, well, we shifted over there, so maybe that doesn't affect things, but By the time we're getting over here, this is position 5 and position 7 that we're comparing. Whereas over here, we'd be comparing position 5 and position 6 to this block of length 2. So these are really different conditions. And it turns out that, so all these conditions are nicely equivalent in the case of Airey expansions, but this fails pretty badly actually in some other cases. So just to give an example, there's a recent paper out with, by Joseph Van de Heij and one of his co-authors. So he says basically that if, so this is Van de Heij plus Pearson. And this is on the archives, so I don't think this has been published yet. I think it might be accepted for publication, but I forget where. But we say that if x is continued fraction normal, and I haven't said what that means yet. It's not really central to the talk, so if you know what it means, it's fine, but if not, don't worry about it. It's some sort of notion of normality. And let's say x is just given by a1, a2, a3, and so on. Say those are the partial quotients. Then, for all r and for all integers m greater than or equal to 2, we have that AR, AM plus R, A2M plus R, and so on, is not continued fraction normal. So this is really saying something very sharply different, right? So this is really kind of analogous to AP normality. We'll say this is AP normality of type 2, what Furstenberg did, what Furstenberg defined. And what we're really saying here is if you're continued fraction normal, then you're not, say, AP continued fraction normal of type 2. In fact, in a very bad way, that bad things happen along every single arithmetic progression. So these types of questions aren't necessarily trivial. So, so the next thing I wanted to get on is, so we'll be dealing with some of these things with Cantor series expansions, which I'll define a little bit later. Another thing that I wanted to get at, which is fairly simple, is really just kind of an exercise in the case of Airey expansions, but some kind of crazy stuff happens when we go to Cantor series expansions. So we say that definition, x is normal of order k in base b if all blocks b of length k occur with frequency 1 over b to the k and the B Airey expansion of x. And we're going to write the set of these numbers as just n sub k of b. So really what we have is if we write n of b, if this is the set of, say, normal numbers in base b, really this is just going to be the intersection over k of the natural numbers of n sub k of b. So I'm going to write something, and this can just be taken as an exercise. It's really, really, really easy to prove. We have the following. We have that, so clearly if, so let's say just exercise, if x is a normal of order k in base b, and x is normal of order 1 in base b, and normal of order 2 in base b, and so on up to order k minus 1. So in other words, say imagine if in base 10 you have all the blocks 0, 0, 0 through 999 showing up with the right frequency. Well, then all of just the individual digits 0 through 9 do also. So this shouldn't be anything too surprising, but I'm just emphasizing that we have this. I wanted to mention another fact. and this is due to D.D. Wall and his PhD thesis. X is normal in base B. If and only if the sequence b to the n x is uniformly distributed mod 1. So this is really, really easy to prove, but it's really, really, really important. So to me, this is really kind of the most important fact about normal numbers, that we really have this dynamical interpretation here that, okay, well, we have a shift bx mod 1, and so you can really formulate normality. You take this sort of combinatorial or probabilistic sort of way of phrasing it with number of blocks of digits occurring, and you can rephrase it really in this dynamical language. So, so what you really have is p sub b of x is bx mod 1. And you can really say that, okay, x, this transformation here is invariant and ergodic with respect to the Lebesgue measure, and you can just say that x is normal in base b if and only if it's a generic point. So this gives, as mentioned, continued fraction normal over there. This gives some suggestions of ways to define normality for some other expansions. So for example, for continued fraction expansion, you have, I'll just write this down over here. Say for continued fractions, okay, what do we have? We have our map, our shift map is going to be tx is, say, 1 over x mod 1. And for simplicity, let's just say, assume that x is, let's say, just in 0, 1 minus the rationals. That'll be the easiest way to do it. And there's some measure, Gauss measure, that we can define on intervals as follows: 1 over log 2, integral over I of dx over 1 plus x. And so this measure, it's not really guessable at all, where it's not that complicated once you see it, and you can check all these properties without too much difficulty, but coming up with it's a little bit hard. And so you can prove that, okay, well, mu, by the ergodic theorem, mu almost every x has a property that t to the nx is mu uniformly distributed mod 1. And then clearly mu is equivalent to Lebesgue measure, so they're sharing the same zero measure sets. Because really this is we have this normalizing constant right here, but this is pretty close. It's kind of weighted a little bit more in some places than others. And so from there, well, okay, so if we define normality to be some x and some generic point of the system over here, then you can pretty easily define the frequencies of blocks of digits like you would with a B-array expansion. So, how often does the digit 1 show up? Well, you know that you have a partial quotient of 1 for your continued fraction expansion anytime you hit the interval, let's say 1/2 to 1. So all you need to do is you need to put this in the Gauss measure. And this is going to be, I think it comes out to 0.415, something like that. So it's about 41.5%. And it decays quadratically. Like if you have a larger partial quotient, let's say it's 2, 3, 4, and so on, it's going to go to 0 quadratically. Okay. So, and you can do this for a Laurent series. It's fairly simple there. You have a shift and you have a Lebesgue measure, so that works out a lot nicer. Beta expansions are a little bit rougher, so you have this Perry measure. Renyi showed that this for the beta shift, so that's in the case that you have, say, some real number, beta greater than 1, and you have your map T sub beta of x is beta x mod 1. And so this is actually quite a bit harder than just dealing with the case where beta is an integer, because we just have a real number, and Renyi in 1957 showed that there exists some invariant and ergodic measure for this that's equivalent to a Lebesgue measure, and then Perry and Galfond in 1960 individually came up with exact expressions for this measure. And so this can be done a lot. And we're going to have to, this will motivate some of what we're going to do for Cantor series expansions. So another thing I wanted to mention, we haven't actually given any examples. We've been talking for a little while, and we haven't given any examples of normal numbers. And so it's going to really be important what we consider to be an example. So I mentioned, of course, Lebesgue, almost every real number is normal, not just in, say, base B, but all bases. So it's natural to say, okay, well, we have this existence proof that follows by strong law of large numbers or Birkhoff-ergodic theorem or any, there's actually several other ways to do it. But what's an example? So the simplest example of a number that's just normal, say, in base B is the Champernowne construction. We'll write it in base 10. So this is due to Champernowne. And this is in 1933. And it's just sort of the simplest thing you can write down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2, and so on. And by the way, this is transcendental also, I should mention, but I'll say a little bit more about that in a second. But this is sort of a good, let's say, very challenging exercise you can give to someone without knowing too much. But it's really kind of harder than it looks to just prove directly from the definition that this is normal. But it's doable. You don't use any advanced techniques. I think it was 1935, Besekovich showed that if you take the digits of the squares and concatenate them, you get a normal number. And just to be clear with this also, like you're not, there's no claims that this real number is normal in base 17, right? Because your base 17 expansion is going to look like something totally crazy. So you have really just kind of a sequence, in this case the natural numbers, and a base, and it maps to some real number, and we only claim it's normal in that base. This also, by the way, has a very interesting continued fraction expansion. The partial quotients just kind of get large out of nowhere really quickly. So I think it's on Math World that you can look and see this. So I'll just mention a little bit more. So Copeland and Erdős, and this is in 1946. They looked at prime numbers, 0.2, 3, 5, 7, 11, 13, 17, and so on. And why is this normal in base 10? It really just has to do directly, it just comes directly from the prime number theorem. So they really proved a more general result. If you're concatenating digits of some sequence that's going to infinity, and if there's enough of them there, I'm not going to write down the condition now, then you get a normal number. And this just barely satisfies their condition that since we have the number of primes up to n is about n over log n. But it's entirely a combinatorial argument. So there's, it's just directly counting. It's, very well done counting. And I'll just mention one more because we can kind of go on all day about this because there's tons of results like this. So just mentioning really kind of some of these early results. If you take point P of 1, P of 2, and I'll say what these are in a second. Suppose P is a positive increasing integer valued polynomial, then you can take the digits and concatenate them and so on. And this uses some more technology. I don't want to get into exactly what's going on in this one. But it's not really the same type of argument as the other ones. And this has been improved a lot. I don't want to, there's been, I think, dozens of papers of this type since this has been done. This is, of course, I forgot to write 1952. So you can take like, not just integer value, but you can have you can take greatest integers, you can throw in prime numbers, so you have polynomials evaluated at primes, you can do things with entire functions and some other number theoretic functions. It's been, a lot's been done on this. But they're still missing something. All of these examples are just normal on the base that they're given. So what if we want something that's normal on all bases? And as it turns out, that's a lot harder. So Sierpinski and Lebesgue, they had sort of these very they're not explicit examples. They had sort of, I think Kuipers and Niederreiter calls them, well, I forget what the word they use, but it wasn't really the sort of construction you do here, and I think you need axiom of choice and some other things to actually do it. But you don't get something you can actually write any digits out. So in a sense, it's kind of an example. They're saying, okay, something that would come from this process gives you a normal number, but it's not something you could say write up a program for to spit out digits. In fact, these aren't computable numbers. And so our condition for what's going to count as an example is that it's a computable real number. And this is something I don't want to get too much in the definition of this, but roughly what you just think of, if the number is computable, it means that you can write a computer program to spit out as many digits of it as you want. And when we think about it, okay, how many real numbers are going to be computable? And it's really not that many, because a computer program is finite, so you have at most countably many computer programs, well, there's uncountably many real numbers. So it's really not the typical thing that you have a real number that's computable. But there are a lot of examples of computable real numbers that are pretty simple. So something like pi, for example. This is computable because, well, this is sort of the worst way to do it, but we have this formula for inverse tangent 1. Well, we can just use a power series here. 1 over 1 minus 1 over 3 plus 1 over 5 and so on. So you can very, very, very slowly compute digits by using this. And it's the same thing for like e. We can use e is the sum of 1 over n factorial. It'd be pretty easy to write it's pretty easy to write just a simple computer program to get digits of these. You have to be able to keep track of them, but there's a lot of stuff that's just not computable. So this isn't something that we can assume in general. And since there's only countably many, how do we even know there's a computable number that's normal in all bases? And so actually Turing, Alan Turing in the late 1930s had an unpublished manuscript where he actually constructed an example of a number that's normal in all bases, that was computable. The algorithm was extremely, extremely slow. It's doubly exponential in time. And so it's not something you'd really practically use to compute too many digits of this number. But this has been improved a lot. So Veronica Betcher and her co-authors say she's been pushing a lot of this stuff with computable real numbers and absolutely normal numbers in 2013. So this is, say, doubly exponential. There's a running time. Here we can do polynomial. And it's natural to ask, okay, polynomial, what degree of polynomial? And it turns out you can get it as close to quadratic as you want, but the closer you get your algorithm to quadratic, the more discrepancy you lose. So there's a trade-off on it, but it's still, of course, way, 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 way better than doubly exponential. But it's, of course, much harder than just writing out something like this. But the point is they have these computable numbers, and this has been pushed. Like there's some other properties they've been able to require on these numbers and all that. The last thing I want to say about just standard normal numbers before we go on to Cantor series is that there's still a lot of open questions with these. So these numbers like square root of 2, pi, e, anything that is naturally occurring, whatever naturally occurring means, it's totally open. Are these normal in base 17 or really, they're probably normal in every single base. But this is something that there's just no chance, I think, anytime soon of there being proof of something like that. And it's really kind of natural to say, okay, this is really an artificial construction. This was just really made for the purpose of being normal. So these would be very interesting things to have. And I'll just write one more. Let's take powers of 2. 0.24, and this is in base 10. 8, 16, 32, 64, and so on. This is also an open question too. Is this a normal number in base 10? So it's probably kind of hard, is my guess. Okay, so what we're going to do is we're going to talk about Cantor series expansions. And so Cantor series expansion is a generalization of the decimal expansion. So what we're going to be doing is, rather than doing what I did, say, with beta expansions, where we can take a non-integer base, I didn't go into too much detail on it, but we can change our base at every step. So we let, say, q equals qn. We're going to think of these as, this is a sequence of bases. So these are integers greater than or equal to 2. And so then it turns out that, say, any real number x is going to have an expansion in the following form. We can write x is equal to e naught plus the sum of en over q1 to qn. So these are going to be our digits, and we're going to say that en is going to be in the set 0, 1 up to qn minus 1, and en is not equal to qn minus 1 infinitely often. So we have the same sort of situation as we had before, where we have sometimes 2 expansions for certain numbers. Really, it's kind of the terminating expansions that have 2. And this is just saying, well, if we have a choice, we're going to pick the terminating expansion. Right? We're not going to pick the expansion that does something analogous to ending in all 9s. So like in decimal, we have 0.499999 repeating is the same as 0.5. In this case, we just pick 0.5. And so why is this called a Cantor series expansion? And so the reason is that, okay, we have this familiar sum, the sum of 1 over n factorial. Well, what is this? This is 2 plus 1 over 2 plus 1 over 2 times 3 plus 1 over 2 times 3 times 4, and so on. Well, what do we really have here? We really have, in this case, this is E0. E0 is equal to 2. And then we have En is equal to 1 for all n bigger than 1, and Qn equals n plus 1. Right, because we start on base 2, and then we go to base 3 and base 4 and so on. And so what Cantor was originally interested in was sums like this. When are they irrational and when are they rational? And it's really probably a hard problem. It's not really clear. At this point, there's going to be, you give some arbitrary base. What's the condition on when you have a rational number or not? In the case where Qn is constant, we have a very simple condition that a number is rational if and only if, say, decimal expansion, right? Which is when Qn is equal to 10 for all n, if and only if the decimal expansion is eventually periodic. So this isn't really what we're going to focus on, but this is really kind of the original motivation. And what we're going to really care about is normal numbers. So this was originally studied by Erdős, Rényi, and Turan in the 1950s, and then a bunch of other people have worked on it too. They were really just kind of making the initial definitions and working on it and deriving some properties. So I'm just going to kind of skip really talking too much about the history of this, and I'm just going to kind of give what the definitions we're going to be working with are. So I mentioned, these equivalent definitions of normality and base B. So let me just write out kind of the simplest thing we can start with. So remember we have this equivalent condition that a number x is normal in base B if and only if b to the nx is uniformly distributed mod 1. Well, let's write this. We're going to say definition. Say x is Q distribution normal if, say, the sequence Qn to Q1x is uniformly distributed mod 1. Okay. And so this can be, I think this is a very natural definition. We're looking at the closest thing we have to a shift. And I just want to remark right now that what we're really doing is we're dealing with a non-autonomous dynamical system. So our what we do, our transformation really at step n is going to depend on n. We're not just iterating the same transformation over and over again. So we have some other interesting difficulties that come up from that. But it's not difficult to show using the sort of well-known result of Weil that Lebesgue almost every real number is going to be Q distribution normal. It doesn't matter which Q you pick. But I do want to remark that not every, or there are actually no x that are Q distribution normal for every single Q. So this idea of a number normal on all bases, in this sense, it just doesn't exist. And there's just too many. It's really morally the idea is there's just too many bases. But the proof is it's really kind of an exercise. You can take, it just follows from the fact that irrational circle rotations are dense in the unit interval. You can pick given some irrational x, you can pick some q such that the sequence of shifts just stays in the interval 0, 1/2 is all it really is. And also along the line of this being a shift, keep in mind you're also shifting your base as well. You're not just shifting the digits. And we'll give another definition. And this is going to be really what we're kind of going to be more interested in. But I'm still writing basically all these definitions because I think they're still relevant to what we're going to be talking about. So we're going to define, say Qnk to be the sum from j equals 1 to n of 1 over qj plus 1, qj plus k minus 1. So we can think of this in the case that Qn goes to infinity and at a slow enough growth rate. This is going to be important. We're going to only add for this talk. We're really only going to be caring about basis Q where we go to infinity and sufficiently slowly. We can think of this as an approximation to the expected number of times you should expect to see some block of length k up to position n. And we're going to define this function n sub n q of b comma x. This is just going to represent the number of times that you see the block B in the Q Cantor series expansion of X up to position N. So we're going to say, and I'm going to go through this a little bit slower than our definition of normal number, because it's going to be important what we do with this. So we're going to say that x is q normal of order k if for all b, where the length of b equals k, we have the number of occurrences of b and x divided by q and k goes to 1. Now this is, and I want to emphasize that the way we're writing this, it's different, it looks a little different than what we say for the Beer expansion. We'd say, well, the frequency, the number of occurrences up to n divided by n goes to some number. But if you just rearrange this a little bit and kind of put that number over here, it's really the same thing. But we run into this extra problem that it wouldn't work the original way, because if qn is going to infinity, well, you kind of get this idea that every digit should be showing up with the same frequency at every step, and at each step rather, each admissible one. And well, if qn is going to infinity, then the frequency of really anything should be going to 0, and you don't really get any information. But if we make it grow like the expectation, then we actually get some information. And we're going to call this set n sub k of q. And we're going to be very interested in these sets. And so we say that x is q normal, right? If x is a member of the set, we'll say n of q, which we're going to define to be equal to the intersection over k and n of n sub k of q. Okay, so for q normal of order k for all k. And there's another definition we can take that's kind of similar to this called ratio normal, but in interest of time, we'll not talk about it right now. Okay, so this goes back to this pretty simple thing I mentioned earlier that all of a sudden gets a lot more complicated. Let's say that you're normal of order 2. Are you necessarily going to be normal of order 1? The answer is no. If you're normal of order 17 and normal of order 2, must you be normal of order 5? Once again, the answer is no. And part of the main goal of this talk is going to be to give some sort of explanation as to why this happens. It's really, really, really bizarre that that could really be the case. And we want to also be able to generate examples of, say, pairs x and q where we have these properties that you can come up with, being normal of some order, not another. This is a little bit of a spoiler alert to say one of the main theorems, but it's possible, for example, to come up with base q and a real number x that's normal of all prime orders and not normal of all composite orders, for example. There's a lot of different ways to do this, and there's a conjecture. And part of the purpose of this talk is going to be to show you sort of where we failed this conjecture. We can kind of get kind of close to it. For all, let's say S subset of n, there exists a pair x and q where x is going to be a member, let's say intersection over k and s of n sub k of q minus union over k not in s of n sub k of q. So in other words, we can take any arbitrary we think we can take any arbitrary partition of the natural numbers and get something normal of order k, and not something and where k is in s, and then not normal of anything that's not in s. And we very, 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 very strongly believe this to be true, but there's some problems that come up that we'll say later. I also want to remark in terms of Hausdorff dimension that you can get these sets to be large in the sense that they have full Hausdorff dimension for a lot of bases. So we're not quite sure how you would do this for every single base, so this is something where it's less clear what needs to be done to get the result in general, but it seems to be very likely that you don't need to necessarily say there exists a q. You could it's probably true that for all q, where qn goes to infinity, and at a slow enough growth rate, in particular we want all of these things to go to infinity, as n goes to infinity, then we should be able to get that the Hausdorff dimension of this set is 1. That's our conjecture, and I'll lead up to what we think is going to happen. The other thing too that's relevant, so we spent a lot of time talking about AP normality of type 1 and 2, So it's a natural question to ask, okay, well, what about Cantor series expansion? What if we modify our definition of normality to look at what happens along arithmetic progressions? And does it necessarily happen to be the case that normality and, say, these other analogs of AP normality end up being equivalent? And the answer to that is also false. We really kind of get both of these results at the same time from the same construction. And we also want, not just existence of x, right? We also want, like I said, if possible, computable examples. And the main thing is going to be that the indicator function on S is a computable function. So I'm going to sketch the proof of a simple case of this. And this will hopefully give an idea of what you really want to do in the general case. And then I'll sketch a proof of it, and I'm going to show sort of what when we encounter a problem, what we do to get around it, and where we get sort of a theorem that's not quite as strong as what we want to have there, but I think it's eventually going to be doable. This is, of course, nowhere near as hard as some of the things like showing that pi is normal, and then base 83 or something like that. So, so let's just start out with a simple case. So let, say, P be a slowly growing, let's say very slowly growing, basic sequence. Let's say monotone, basic sequence. And let's say Pm goes to infinity. So it's going to infinity, but it's going really, really slowly. And the property this is going to have is that it's going to be locally constant, really. You can kind of look at any place, and the bases aren't changing too much. I also wanted to find a function. Let's say we have for, say, basic sequences, say A and B, we define, say, a function psi, let's say AB of x. And how are we going to do this? So we say that suppose if x is equal to points E1, E2, E3, and so on in base A, we define, say, psi AB of x to be the sum from n equals 1 to infinity of the minimum of, let's say, En and Bn minus 1 over B1 to Bn. So what this function is doing is you're basically transplanting all the digits from your base A expansion into your base B expansion, and you're truncating them if they get too large. So these functions themselves are actually already even interesting. There's a lot of interesting fractal-like properties they have. There's a paper I have that deals with this. We're not going to talk about that right now. But the main thing that's important is under some fairly minor conditions, if both An and Bn go to infinity. So if, say, An and Bn go to infinity and plus other minor conditions, we have the following. That the number of occurrences in base A of B comma x is going to be the number of occurrences in base B of B comma psi AB of x plus big O of 1. So this is a theorem it's not too difficult to prove this, but it turns out you can do a lot of stuff really, really easily if you just know this fact. And we're going to be using this heavily in our construction. Okay. So this is really important here. And so it says the psi BQ function doesn't really change your digit or block counts too much, but when you change to your new base, your expectations can change a lot. So these expected value-like terms I mentioned, these Q and Ks, those can change a lot when you go to a different base. So going back here, we have a slowly growing monotone basic sequence. And so what we're going to do, okay, it turns out that, and you can prove as a consequence of the strong law of large numbers, that if this is the case, then you can cook up, then there exists, just by measure theoretic arguments, it's a set of full measure, a real number x that is not just p normal, but also p AP normal of both types. And I don't want to write the definitions for p AP normal, they're in the paper that I'll have on the archive pretty soon, hopefully, but they're kind of technical. I mean, it's really just the same idea as what the definition of Borel and the definition of Fürstenberg is, but in order to make them precise, you need notation, and it's just really not worth writing on the board right now. So we're going to say So let x be P normal, P AP normal type 1, and P AP normal type 2. Okay. So we start out with some number with this property. And so if x has this property, well, let's just even think, what's going to happen at a typical position? So if we consider some sort of block and we want to look far enough out, let's look at positions, and I'll say why this number in a little bit. Let's say look at positions starting at, say, a position that's 1 mod 6, and we're going to look at a block of length 6, say in a typical normal number. So we're going to have some bases, Pn plus 1, let's say En, En plus 1, and so on up to En plus 5, Pn plus 5. Okay. So we know since P is this basic sequence that's really slowly growing, just imagine log, 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 log of n. It doesn't have to be that slope, it's something like that. Then what's going to happen, well, if you look at some arbitrary position, it's really, you look to the right 5 places, you're going to still have the same base. So what we can really say is we can really say that Pn equals Pn plus 5 equals alpha. Now we know if n goes out really large, this is going to, this isn't going to be the case for all n, but this is just a little bit of a hand-wavy sketch of what's going on. So we can really say that these are all equal to alpha. Now let's ask ourselves then, let's say we have a block of length 1. So I'm going to go here just to keep this still visible. So we should ask, so for a block of length 1, how many times should we expect to see it? Well, basically the idea is you want to let n be large enough so that alpha is larger than the digit in this block. But once that's the case, well, what's the expected number of times you see it? Well, it's just going to be 1 over Pn plus 1 over Pn plus 1, and so on to 1 over Pn plus 5. Well, this is just going to be 6 over alpha. Okay. Let's say we want to look at length 2. It's going to be 1 over Pn plus 1. And so on up to 1 over Pn plus 5, Pn plus 6. Okay, well that's just going to be 6 over alpha squared. And let's say length 3. It's going to be 6 over alpha cubed. Okay, now at this point I want to actually say, what do we really want to require? So we're interested in losing normality and AP normality, but let's say that we want, say, normality, say of order 1 and 3, but not 2. So keeping these in mind, what we're going to do is we're going to somehow transform this number. We're going to somehow cook up a new base where we have roughly the same digits, but these expectations match for the first and the third one, but not the second. So that's just the rough idea of what we're doing. So I'm going to define the base right now. And I'm going to be playing it a little bit fast and loose with greatest integers and things like this. So, since this is just a sketch of a proof, we're not going to be fully rigorous. This is, fully rigorous in the paper. So we're going to do this the following. We say Q equals Qn. And we're going to have some constants in here. We'll define the constants later. So we say that Qn, let's say Qm really, because we kind of fixed n over there. Qm is default as what? In the case where m is congruent to 1, 2, or 3 mod 6, we're going to say that this is going to be Pm divided by Ci, where m is congruent to I mod 6. So we have some constants. We're going to cook up these constants later, so you'll see where these are relevant. And let's say 2 to the m times Pm, where m is congruent to 4, 5, or 6 mod 6. So what we're doing is that half of these, we're just scaling them by some sort of constant factor, and the other half we're just blowing them up like crazy. Okay. So we have some new base defined like this, and we'll just ignore the fact we need greatest integer and min and some other stuff there, it doesn't matter. So then we want to say is we let y equal psi pq of x. Okay. So this number I claim we're going to be able to cook up if we choose the CIs appropriately. We're going to make it have these properties we want, where it's going to be normal of order 1 and 3, and our new base, but not normal of order 2. So supposing we have some new base q, well, what's going to happen? Let's say we're looking at position n again. Let's say we have qn up to qn plus 5. Okay, well, how often do we expect to see a block of length 1? So for length 1, we expect to see a block that's going to be 1 over qn plus 1 over qn plus 1. I'm going to write this one out in a little bit of detail. Qn plus 3 plus 1 over qn plus 4 plus 1 over qn plus 5. We expect to see it about this many times. Well, our qn's, right, these are defined in terms of pn. So this is going to be what? This is going to be approximately. Well, we have qn. Well, n is congruent to 1 mod 6, what we fixed over there. We're just keeping that fixed. So this is going to be c1. This is going to be pn divided by c1, or in other words, this is going to be c1 over alpha. Similarly here, we have c2 over alpha, and c3 over alpha. And then these right here, these are just blown up like crazy. These are some power of 2 times alpha. So we can just consider these to be plus some sort of lower order terms. That's the whole reason we're doing this. We don't care about them. Just blow them up like crazy. And so this is then going to be approximately c1 plus c2 plus c3 over alpha. Okay. Well, what happens when we consider length 2? So we're actually going to have fewer terms because we end up pairing a qn plus 2 and qn plus 3. Well, that's a lower order term because we have a power of 2. So for length 2, what are we going to get? It's just going to be c1 c2 plus c2 c3 over alpha squared. Okay. Still, we haven't defined these constants yet. And then let's say length 3. We have c1 c2 c3 over alpha cubed. So what can we do now? Remember, the original goal that we're going to have is some base q, where we have this number, say y, that's normal of orders 1 and 3, but not 2. So what we're going to do is we're going to solve the following. Let's say, remember that these are, I think I erased it, but we want these to be 6 over alpha squared, 6 over alpha cubed, 6 over alpha. Right? So we want to solve c1 plus c2 plus c3 equals 6. We're keeping normality of order 1. Okay? We'll see precisely how this works in a second. C1, C2 plus C2, C3 equals 8. The reason for 8 is, well, I know in advance that there'll be a nice solution that isn't too ugly. But we want something that's not 6. And it turns out that 8 just works out perfectly. Then we have C1, C2, C3 equals 6. So what we have here is if we have this new base, remember that the number of times that some block B is going to show up is really about the same. You know, we have this theorem that I had about these psi pq functions. We get mapped to, you know, some number where you have about the same block occurrences. But these expected values we see are going to change depending on your base. So we're trying to cook up a Q that has a different sort of expected value coming from this. And so if we satisfy this equation, and if these numbers C1 through C3 are sort of physically meaningful, then we can actually have this base defined. And so for example, if we have only complex solutions, then we don't get anything. But it turns out there's actually a really nice solution here. We have a solution is, let's say, C1 equals 3, C2 equals 2, and C3 equals 1. It does not usually work this well, let me emphasize this. So I'll say a little bit about that in a minute. But using this, what we can do is we can see, okay, well, our new base, but just by that theorem, we have a number, you know, because we started with a number that was normal in base P, and we map it over, well, it's no longer normal in base Q because of this. And it also turns out really just, I mean, almost due to luck that you also lose AP normality as well. So if you look at expectations along arithmetic progressions, things kind of fail as well. So I'm not going to work that detail out on the board right now, but the same thing happens. So now you can imagine, like, okay, let's say that we wanted to do this for, say, some arbitrary partition. So what we could do is we can kind of look at a t by t system and then solve that and keep doing that for a while, and then go to some larger value of t, and then just keep doing this again and again and make the construction more complicated. And it's not really clear that this works. So I'll say basically 100% certainty, we know what happens to the general system. I'll write the general system down. And I'll tell you what we know is going to happen, and this is, we've run a lot of programs on this, and it doesn't seem like there's any reason to expect that there's going to be any change in behavior. But we look at the general system, C1 plus C2 plus CT equals, and I'm going to put a little perturbation term in here, 2 plus epsilon 1t, C1 C2 plus C2 C3 plus CT minus 1 CT equals 2 plus epsilon 2 times t. And so on down to C1 through CT equals 2 plus epsilon t times t. Okay. Now, I just really want to emphasize, remember, just like in this original system we have here, we don't have all possible combinations. This kills a lot of symmetry. So this really ends up being kind of a hard thing to deal with. Conjecture. If, say, epsilon I equals 0 for all I, then this system has a solution, say C1 through CT, that's in the region t to t plus 1, cross 1 to 1 plus 1 over t minus 1 to the t minus 1. And if this is true, then we can just basically do this thing where we modify the construction and everything works out perfectly. The problem is actually showing this, we have no idea what to do. I mean, there's been some proposed ideas, but, and with these epsilon 1 through epsilon t terms, these are just these small perturbations. Basically, all you do is you have to argue, okay, if you have a solution here, you just got to argue that the solution doesn't really move around too much, which I don't think is going to be too difficult, but actually just getting this, in the case, the simpler solution where we only have 2 t's on the right-hand side, this is, I think, very difficult. And I want to remark, okay, you can do this by hand for the 3 by 3 system. It comes out, it's a much harder solution than if we just have 6, 8, 6. If you have, 6, 6, and 6, it works out. With basic algebra, but it's still some kind of nasty, it's not too bad, but it involves a lot of square roots and things. We went in Mathematica and looked at the 4 by 4, and it's already getting a lot worse. So if you look at 4 by 4, you get some sort of 10th degree polynomial, and you take one of the roots of that 10th degree polynomial, and then all these terms, say in that case C1 through C4, can be expressed as polynomials in that root. And then the output just gets insane when you go to the 5 by 5 systems. So I really think any sort of exact nice solution like this is really probably hopeless in general. And even if you were to get some sort of nice solution in radicals or something like that, which I think is not going to be possible, it's really not going to give any insight to which region these land in. So for example, if you can get only solutions that have at least one of them being negative, then it doesn't give you anything useful here. So, but we really have no doubts at this point at all that there is a solution for all t in this region. It's just a matter of proving it. So, so what I want to say is what we actually did, and this will be the last thing we talk about. I'm not going to get into state all the theorems because there's a lot of fairly strong things that are proven here, but I just want to basically say what we did to kind of attempt to get around this problem and where it causes some issues. So rather than trying to approximate solutions, because we really do kind of know approximately what they are, you can go for large T and kind of figure out, okay, it's probably here. We can do some type of linear interpolation or anything like this. Anytime you do something like this, introduces some sort of error. So I want to write out what our weaker version of the theorem is. And so I need to define this thing first. So we want to define, say S, that's a subset of the natural numbers, is almost closed under addition. Under addition. if for each, say, k and s, the set, let's say s minus k, intersects n minus s, has density 0. So let's look at this condition for a second and see what this means. So what we're really saying is that you take the set S and you shift it over by k and intersect it with stuff that's not an S. What it's really saying is that we're really kind of close in some ways to being a subsemigroup of the natural numbers. So in particular, any subsemigroup would have this property. And that's why we say almost closed under addition. And the theorem is basically that we can do this argument that I did. Well, not that exact argument, but the theorem holds at least. We'll have a slightly different argument for any s that's almost closed under addition. So I mentioned a bit earlier that we can take numbers that are normal of all prime orders and not normal composite orders. Well, you can check and see really any set of density 0 satisfies this condition. So it works out. And so I'll just give, so any set of density 0 or 1. We can also have sets of density that aren't 0 or 1. So for example, we can take the union over k in the natural numbers of k squared plus 1, and so on up to k squared plus greatest integer of gamma k. And this has density equal to gamma over 2. So there's some other things that satisfy this condition. It's not a totally boring condition by any means. But it's not nearly as general as we want it to be. Okay, so let me say what we're going to actually do, and this is going to get a little bit more technical. So here's going to be our approximation scheme. So we want to look at sort of step t. So we're going to do some sort of, kind of going to be approximating the solutions. What we're really actually going to be doing is going to be putting in some sort of substitute values for these t's here. And as t goes to infinity, we're going to get closer to where we are on the right-hand side. Or really, rather, the ratio between this and the right-hand side goes to 1. So we're not actually really approximating solutions, but we're getting some sort of convergence going on here. And so you can fix, say, some kth row or something like that. And we actually are going to be bounded away by the actual solution sometimes. But it turns out that it's going to work out, but we get some error term that's introduced that puts this restriction that we need to be almost closed under addition. So here's what we're going to have. Our approximation are going to be ct comma I is t times 1 plus epsilon. And epsilon is just going to be some, we'll just say 1/10 or something like that, it doesn't matter. 1 minus indicator function on s of 1. If this is if I is equal to 1. And then we have 1 plus epsilon times indicator function s of I minus 1 minus indicator function s of I. And this is for I greater than 1. So what we're really doing here is we're taking t and then we're perturbing it by some amount, by some multiple, depending on whether 1 is an s or not. And then the other ones, we're just basically taking 1. You can imagine this just being 1 times 1 plus epsilon to this power. And then we're maybe perturbing it based on what happens nearby it. And so these are certainly not going to be approximating solutions because we can be bounded away from 1. So we'll just like this, we'll just take epsilon equals 1/10, which works. And this one also, this might be quite a bit bigger than t, it might be some multiple of it. But it's okay, it ends up working out. So here's the claim that we're going to prove, and this is just going to give kind of some idea, mostly just where the error term comes up, and then we're going to stop after that. I'm not going to get into what you do to get Hausdorff dimension. There's a certain trick you can do to get the Hausdorff dimension of these sets as large. So the claim is going to be that the limit, as t goes to infinity, of the sum from I equals 1 to t minus k plus 1 of ct comma I through ct comma I plus k minus 1 divided by 2t is equal to 1 if k is an s, and not equal to 1 if k is not an s. And when I say not equal to 1, the limit might not exist. So all we care is that the limit's not 1. So this is exactly what we want. If this ratio goes to 1, then we're normal of this order. You're looking at some k. And if it goes to something that's not 1, then you're not. So how do we show this? So we need to define a couple things. So we want to write. So this will be a little technical, but I'll kind of say where this is coming in. We say that ATK is equal to the sum from I equals 2 to t minus k plus 1 of the indicator function on S of I minus 1 minus indicator function on S of I plus k minus 1. Okay. And we want to say that BTK is going to be equal to the cardinality of the set where, say, 2 is less than I is less than t minus k plus 1, such that we have that 1 sub s of I minus 1 minus 1 sub s of I plus k minus 1 is equal to minus 1. And this looks like a strange condition, so what does this or strange expression, so what does this actually mean? This means the number of times I is not a member of S, and I plus k is a member of S. Okay. And this is, of course, for I between 1 and t minus k. Okay. And so, once again, okay, so I said this is strange, but there's a really important property. There's going to be some error term in terms of these values that come up. And we note that following, let's go up here. The BTKs are going to be the particularly important ones because this is going to be where the condition of being almost closed under addition comes in. So we note the following, that we have S almost closed under addition. Right, this is equivalent to saying that limit as t goes to infinity of btk divided by t is equal to 0 for k and s. So it's really just, this is where it's going to come in, because this is going to be an error term that comes in our calculation, and we want this term to go to 0. And that's going to happen for k and s whenever s is almost closed under addition. And also, the absolute value of ATK is less than or equal to 2k. And this is just because it's a telescoping sum. So you can check and verify that you get a lot of cancellation here, and we have at most 2k terms that are as big as 1. So it's not really so bad. So what we want to say next then is, okay, we have this sum here that we want to estimate. So starting out, we have that the sum from I equals 1 to t minus k plus 1 of ct comma I through ct comma I plus k minus 1. Okay, this is just going to be a big mess. So I'm going to actually skip writing this all, but let's just say through combining terms and using some telescoping properties, this is going to be equal to 1 plus epsilon times 1 minus 1 sub s of k times t plus the sum from I equals 2 to t minus k plus 1 of 1 plus epsilon to the 1 sub s of I minus 1 minus 1 sub s of I plus k minus 1. And so like I said, this is combining a lot of these terms together and doing a lot of cancellation. But we're going to be able to estimate these a little bit then. So next thing we want to do is we want to use the following. So this is just a little bit of algebraic identity that's very easy to verify. We want to use the fact that 1 over 1 plus epsilon is equal to 1 minus epsilon plus epsilon squared over 1 plus epsilon. Okay, let me just first say why we care about this before we proceed. So we have these 1 plus epsilon terms here, and then this exponent can either be 0, 1, or minus 1. If we have a minus 1, well, we still want to count sort of what's collecting. So if we have a minus 1, well, we have some just terms of 1 that show up, you lose some terms of epsilon, and then you also get this other term here. So we're going to be able to count these through these ATKs and BTKs that we defined over there. So let's do this. So we get the following expression. So we end up getting 1 plus 1 sub n minus s of k times epsilon times t plus the sum from I equals 2 to t plus t minus k plus 1 of the following. So let me explain this. Notice that no matter what the exponent is on this term here, we're going to have just a 1. So if we have the exponent is 1, then we have a 1 plus epsilon, where we're contributing both a 1 and an epsilon. If we have a 0, then we just have a 1. And if we have a minus 1, then we have a minus epsilon in that term. So we always have a 1 being added. But what about the next term here? Well, when do we ever see, how many times are we going to see epsilon? Well, we're either adding it or subtracting it or not changing it. And the term that just makes that work out correctly is 1 sub s of I minus 1 minus 1 sub s of I plus k minus 1 times epsilon. And lastly, there's this possibility that we have a minus 1 as an exponent, so we're going to write a term down here. We have minimum, and we still get some minus 1 exponents counted for there. Minimum of 0, 1 sub s of I minus 1 minus 1 sub s of I minus k plus 1 times epsilon squared over 1 plus epsilon. So all these terms are in the sum, and it looks really complicated, but it really isn't. We're just saying how many times we're adding 1, how many times we're adding epsilon, and how many times we're adding epsilon squared over 1 plus epsilon. So we can collect all these terms together. It's clear how many times we have 1. So we'll just copy this one down. We have 1 plus 1 sub n minus s of k times epsilon t. And then we have plus t minus k. This t minus k is just coming from how many times we're adding 1. And then we have a t comma k times epsilon. That's, when we really sum this up, that was what we defined as a t comma k. And then lastly, we have b t comma k times epsilon squared over 1 plus epsilon. Well, what happens here? We want to know, this combines with this right here, that becomes a 2, right? And this term here, well, atk is bounded by k. As t goes to infinity, that whole term goes to 0. But this one, maybe not so much. So if k is a member of S, then this is, well, if k is a member of S, then this term is 0, so that drops out and we just get a t plus t. 2t plus little o of t. Okay, so that's wonderful. And if k is not an S, then it's bounded below by something that's going to be 2 plus epsilon t plus a little o of t. So this is where I'm saying that the limit, it's not that it just isn't equal to 1, it's just bounded away from 1. And so that's where this condition about being almost closed under addition comes in. And so there's some tricks you can do to get one of these computable, one's the Hausdorff dimension equal to 1, but I think we've already gone on long enough, so we'll just stop with that. So.
Stop recording.